Hello friends, how are you all today? Have you ever wondered what are Jacobians and how we can use Jacobians to solve the engineering problems? It's coming up right now. I'm Prashant, technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with Jacobians. Let us consider a following situation. Here, uh, let's consider a diagram. Uh, we are having a coordinate system. On the left hand side, we can see that a circle in red color is being represented over the constant x, y plane. In a sense, the lines of constant values of x and constant values of y are used here to represent the circle. That's one kind of representation. At the same time, what if in some situation I don't want the constant x and constant y values to be present in my system? Instead, I want the other way. That is, I want to represent the same circle, but in terms of constant radius and constant angles denoted by r and phi respectively. We face quite often such scenarios in engineering, and we will be calling it as change of coordinate system. So the overall idea here is to make a transformation from the old coordinates, that is x and y, into a set of new variables. Let's call it as some r comma phi. So, right, we have the old variables. On the right side, I have the new variables. So this, from moving from left to the right side, is what we refer as the transformation. So overall, we have three requirements here. So the first requirement, now whenever we want to change xy to a new set of variables, here I have denoted as r5. Okay, so the first objective is we are supposed to choose a new variable. Okay, one or more variables. I'll write new variables. Okay, we might have denoted as r and phi, but what exactly is r? What exactly is phi? Right? To describe. So why you need to do that? This is to describe the transformation. I'm supposed to do this first, and my next objective is to describe the function in the new variables. What are the different functions? Because here I know that x and y are the constant lines. Okay, constant x value will have a line, constant y value will also be a line. The intersection of those lines give rise to the coordinate system, right? Very similar to that. Now my second objective is to describe the function in variables. All right. At the same time, I have another option, that is the third objective, right, is also to find the partial derivatives. Partial derivatives with respect to the new variables. With respect to the let us generalize this problem, for which I need to consider the following diagram. So in this diagram, we can see two different functions. The two functions are, on the left hand side we can see f of x, y, which let us consider, right, it's a surface, right, over constant x and constant y, the one which we considered earlier. So let me write, this could be the x and the other line could be the y. Okay, now we want to transform. So this is what I want to transform. I just write a t over here with a different color, which is okay. So I want to have a proper transformation. So this is the t. I want to have a t in such a way that I am going to get a new surface. For example, if you consider the previous surface, that is f of xy, but the surface which my intention I want to get now is f of u comma v. All right, so we can see that this in general my x comma y is getting changed to f of u comma v, where u and v are the new variables. There will be something new coming up, like constant values of u and constant values of v, right? Those curves will be there at the bottom. Okay, so for example, here we can see that they are the constant x and y's, which we are seeing here. Okay, very similar to that, I'm going to get a constant maybe u and constant v. So u and v, their orientations are different. For example, u can be the radius, like r, right? Radius increases from some center, you are changing the values of u. At the same time, the v can be the change in terms of the angles, right? So the phi varies, like 10 degrees, 20 degrees, 30 degrees, or any, it can be even in radians. So we understand that the orientations of u and v are completely different when you compare to x and y, which were the original variables. So for example, I try to denote that. In this case, maybe when I move in this direction, right, I am changing u, but maybe v is varying, right? The v could be varying when you move in this direction. So you can see that there is a, right, very clear cut differentiation as that's about when u changes and when the v is going to change. So we need to remember one thing when we do this kind of transformation. The first thing is that the surface which was considered originally will remain intact. So there will be no change in the shape. Okay, whether it can be f of x comma y, this is the old one, or the transformed one is capital F of u comma v, right? So in both of them, right, the surface has exactly same, I can write, shape. So shape is not going to change. At the same time, I should remember one more thing. If at all it's an object, right? If you are representing f of xy or f of u comma v, right? The object in f of x comma y, or I can write capital F of u comma v, right, retains its area or its volume. They are not going to change at any cost. So the ultimate idea here is that whether you use the first coordinate system using x comma y or the second coordinate system using u comma v, right, you should be able to calculate the volume or the area irrespective of which particular coordinate system you are using. Okay, so I'm supposed to get the same answer irrespective of my coordinate system. If the first method gives me an area of 10, right, the second method also should be uh, able to give me the same value of 10. So far, what we studied is we can convert a given coordinate system into any other coordinate system in general. There's no doubt about it. Okay, we can convert into any other general system represented by the two or three coordinates u, v, w, etc. Okay, but since our intention is to mainly to solve the problems related to the field of engineering, what we can do, we can consider only the standard transformations used, right, in engineering as a whole subject. Okay, so they are as follows. So I'll write the standard transformations. Okay, the standard transformations used, which we are going to learn, are on one side I have the x comma y. Okay, so the x comma y values will be are called as the Cartesian coordinates. Okay, this will be converted into three different coordinate systems in general. The first one is called as the polar, okay, and the second one is called as the spherical, okay, and the third one is called as the cylindrical. These three coordinate systems are generally used in engineering dependent on the problem and the type of symmetry that is expected to solve the particular problem. Therefore, in order to convert f of xy to capital F of u comma v, we can use the partial derivative and the chain rule of partial derivatives as follows. Okay, so we start with the partial derivative dou f by dou x. This can be calculated as dou f by dou u into the dou u by dou x plus dou f by dou v into dou v by dou x. Let's say this is equation number 1. Similarly, I can write the partial derivative of the function dou f by dou y is equal to dou f by dou u into dou u by dou y plus dou f by dou v into dou v by dou y. Okay, let's call this equation as equation number 2. Now we have to find out what are the values of dou f by dou u and dou f by dou y? Okay, because using those values only, we will be able to uh, write the required transformations. Ultimate goal is to write the transformation, that is what is u, what is v I'm supposed to write. So the dou f by dou x says how much the function f, the original f, varies with respect to x. Similarly, the dou f by dou y says how much the original function f varies with respect to y. Okay, but since our intention is to represent the same function with respect to u and v, I introduce the terms u and v. Here I introduce u, here we introduce v, and this can be done easily, and it is valid because it obeys the rules of partial differentiation. Now we need to solve the simultaneous equations, equation 1 and 2, to first make it dou f by dou u. Then we'll solve the same equations once again to get dou f by dou u. Okay, all right. So let's simplify like this. I'll try to multiply equation number 1 into, I'm going to get the same terms as the dou f by dou u on the other side. That's for equation number 2. So what I do here, I'll multiply this equation number 1 by dou u by dou y throughout. So this means, right, this gives what? This gives the dou f by dou x into dou u by dou y is equal to, I have dou f by dou u into dou u by dou x into the dou u by dou y plus dou f by dou v into dou v by dou x into dou u by dou y. Okay, let me call this as equation number 3. Similarly, what I do now, I take the equation number 2 and I multiply by dou u by dou x. Okay, this gives me, so the second equation is getting multiplied dou u by dou x. So this is dou f by dou y into dou u by dou x is equal to dou f by dou u by dou y into the dou u by dou x, dou u by dou x plus dou f by dou v into dou v by dou y into dou u by dou x. So I will call this as equation number 4. Now what we can do here is, okay, now we would like to subtract one from the other. Say I'm going to perform 4 minus 3. Equation 4 minus equation number 3 gives this. So I can understand that this will be cancelled, right? So since I'm performing 4 minus 3, I have the terms the dou f by dou y into dou u by dou x. This is the first term, minus the term coming from equation number 3 is dou f by dou x into dou u by dou y, right? So this is on the left hand side, should be equal to, I can see that dou f by dou v is common. So dou f by dou v into, I'm taking the same terms. I can write dou v by dou y into dou u by dou x minus dou v by dou x into dou u by dou y. So how did you get this? Let me repeat. So this term minus this term is this over here. Okay, similarly, I'm performing fourth one minus third one. So I can see that this dou f by dou v is common for both of them. I'm writing it outside. And then the remaining terms, this comes over here, this comes over here. All right. So now I can simply rewrite them to get back to the dou f by dou y. So this is a term I keep on one side. So that is, this implies the dou f given by dou v is equal to, right? I'll write the term on the left side, which is on the top. That is dou f by dou y into dou u by dou x minus dou f by dou x into dou u by dou y. This is the numerator part, whole divided by, I write the denominator, that is, I'll write the term with respect to x first, then I'll write the term with respect to y. Maybe that will be easier for me. Okay, so that is dou v by dou y into dou u by dou x minus dou v by dou x into dou u by dou y. So we can see that out in the equation number 1 and 2, I told initially that my intention is to find out dou f by dou v and dou f by dou v one by one. So in which you can see that we found this first, dou f by dou v. That's over. Now we'll do the similar calculation. So let me call this as equation number 5. Okay, I need to do the similar calculation to calculate the dou f by dou u. All right. So in order to calculate the dou f by dou u, let us first copy down the equations 1 and 2 once again. Right? Let's copy and let's paste it. Okay, I just copied equation number 1 and 2 once again. All right, let's move on. Now, previously I tried to multiply. I try to make these two terms same so that I can cancel them. I can cancel those two terms and I can keep dou f by dou v and dou f by dou v. Now I do the reverse, which means I try to cancel the dou f by dou v. So equation 1, I'm going to multiply with the term, this term. Okay, that is 1 into dou v by dou y. So this gives me dou f by dou x into dou v by dou y is equal to dou f by dou u into dou u by dou x into dou v by dou y plus dou f by dou v into dou v by dou x into dou v by dou y. So equation number 6. After that, now equation number 2, I need to make that also to have the same terms equation number 1, so that you can cancel some terms. All right, so equation number 2, I'm going to multiply with dou v by dou x. When you multiply that, you are going to get this is dou f by dou y into dou v by dou x is equal to dou f by dou u into dou u by dou y into dou v by dou x plus dou f by dou v by dou y into dou v by dou x. I'll call this as equation number 7. All right, now our intention is to find the dou u by dou u, so I can perform equation number 6 minus equation number 7. Okay, it means I'm cancelling these two terms, so 6 minus 7 gives dou f by dou x into dou v by dou y minus dou f by dou y into dou v by dou x. It's on left hand side. This is equal to, I have a common term, dou f by dou u into, so dou u by dou x into dou v by dou y minus dou u by dou y into dou v by dou x. Therefore, I can write the final answer, that is dou f by dou u is equal to dou f by dou x into dou v by dou y minus dou f by dou y into dou v by dou x whole divided by, this is dou u by dou x into dou v by dou y minus dou u by dou y into dou v by dou x. That's equation number 8. Here we got both the dou f by dou u and dou f by dou v. Just for comparison, let me copy equation number 5 and paste it down. Right. Okay. All right. Now I want you to compare the denominators. So dou u by dou x, that is here, dou u by dou x, dou v by dou y, dou v by dou y minus dou u by dou y into dou v by dou x. Yes, they are same. Okay, so in this case, All right. The denominators of both equation number 8 and equation number 5 are same, which indicates that that's the common factor you need whenever you calculate the dou f by dou u and dou f by dou v for any given system of uh, coordinate system. All right, let's proceed. The denominator of 5 and 8 is called as the Jacobian. Okay, therefore, the Jacobian J is equal to, I write the term, that is dou u by dou x into dou v by dou y minus dou v by dou x into dou u by dou y. This is term. Now, actually, if we use the basics of the determinants, we can try to write this as a determinant as follows. Okay, so this is equal to, it's the determinant of dou u by dou x and the dou v by dou x, dou v by dou x, dou u by dou y, dou v by dou y. It's a determinant. Or you can actually, this is same as, because you might find different versions of the determinant in different textbooks. All right, so that actually doesn't matter. Even if you find another version, don't worry, it's same. So that is dou u by dou x, dou v by dou x, and dou u by dou y, dou v by dou y. So ultimately you see that anyway, you are multiplying dou u by dou x, dou v by dou y, it's happening here. And also the other multiplication is dou v by dou x into dou u by dou y. So that's happening like this. Okay, so that's this term, and the other color is this term. So it's happening same way, irrespective of what type of determinant I'm writing. That doesn't matter. All right. So the standard notation for this is, all right, J is actually given by dou of u comma v to dou of x comma y. A very standard notation which we are going to use many times. Why I introduce you to this first? Because we are going to use this to solve our problem. Our problem we decided initially was to convert x comma y into any u comma v, any coordinate system into any other coordinate system, right? We'll see how do we use this Jacobian to do that later.